So, now this is the most difficult task for me to explain this topic. The topic is absolutely simple, but it is difficult for me to it's difficult for me to make you understand such topic because they are beautiful topics, but it lies in the person who is explaining that concept, and so I hope you will appreciate the effort. And if you don't understand, please do contact me. I'll just try what to do. Now we are going to see what's called as the generalized coordinates. Alright. Now, so alright. Suppose we have this configuration. This and this. Suppose I have my u1. This is my u1. This is my u2. I can represent it. So I can represent it in the following graphically. This is my u2, this is my u1, and I say passes to the center. So this is my q1, this is my q2. I define, what I do is I define q1 as u1 plus u2 multiplied by half. So I can say my u1 is what? I don't want to write in terms of q2. I do want to define what's q2. This is my q2. Alright? And q1 is some kind of a center of mass of the system, right? It's some kind of a center of mass of the system. So I chose my generalized coordinate. One generalized coordinate is the center of mass of the system, and other is the separation between u2 and u1. I know you might have some questions, but please do wait for me to finish the explanation, so that I'm trying to address each and every question that you might have, and I'm going to answer that question myself. If you have any other doubt, please do contact me. So, in terms of q2 and q1, I can now define my u1, which is q1 minus q2 upon 2. Similarly, my u2 is equal to q1 plus q2 upon 2. Okay? And this is appreciable. Now, what I need is, given q1 and q2, I get unique u1 and u2. See, it's visible, right? Given q1 and q2, I get unique q1 and q2. See, it's minus sign. And u1 and u2 are nothing but the configurations of the system. Just last lecture, I explained what are the configurations of the systems, and I'm allowed to do such coordinate transformation. This is one of the important things. I'm allowed to do such a transformation. Who's there to stop me? So what I do is, q1 comma q2 actually, what does it actually represent? It actually represents the coordinates of any of these particles, right? Any of these particles. But of course we can interpret the system. Of course there is an interpretation. Say I just told you, say my q2 is the separation between u1 and u2. See? And my q1 is nothing, as I told you, it's the center of mass of the system. It's the center of mass of the system. So I define a generalized coordinate q1 comma q2 of the system. They are my generalized coordinate of the system. See, there is no saying the limit of transformation, of course, and also I need not. It need not to be. It need not to be a linear transformation. There are two things. No limit of transformation, and it need not to be linear. It need not be a linear transformation. So it can be nonlinear. So this implies that it can be nonlinear. So can I define some nonlinear transformations such as S1? I define S1 to be such as q1 square plus q2 square. And I'm defining as q1, I defined S1. So S2 is say my tan inverse of u2 upon u1. So these are my nonlinear transformation. But again, there is no limitations and it need not be linear. Again, these are generalized coordinate system. So one of the things that you appreciate would be an example. So an example is model. Okay, so consider this. We have an axis. Say this is my M1. This is again my M1, but it's an this theta that it makes, and suppose this is my position x1 y1, my position x2 y2. So now for such a system I have 4 degrees of freedom. My DOF is 4. So the configuration space is r to the power n. This implies it is r to the power 4. This implies it's a 4-dimensional space. It's a 4-dimensional space. So my x1, x2, y1, y2, I can interpret as xcm, the center of mass, ycm. So now we have theta, that means and it is happening in the 2-dimensional plane. So see, don't confuse it. The configuration space as a df4, that is implies a 4-dimensional space, but my real motion is happening in a 2-dimension. So as a result, I can use r comma theta. It's happening in a plane, right? It's r comma theta. So my configuration of the system is n-dimensional. My first set of coordinates would be, okay, so my configuration space is n-dimensional. So what are my first set of coordinates? So how do we do? Initially we choose u1, u2. So we initially name each of the coordinates as u1, u2 and so on. I'm talking about general, okay? Now I'm talking about in general. So this was just an example to show you how the configuration space can have the dimensions, can have the following dimensions. How do we use this definition? And also here is the dumbbell. It evolves in mass m1, m2. It has some motion, and x1 and y1 are the positions at this coordinates. y2 and x2 and y2 are lambda of mass m1 in this space, and I told you the motion is happening in a plane, but the configuration space is a 4-dimensional space because of the degree of freedom being 4. So we interpreted that x1, y1, x2, y1, y2 can be reinterpreted as xcm, ycm, r comma theta. So in general, now I'm talking formally, for a configuration space of an n-dimensional, I can have my first set of coordinates, which is written as u1, u2, un. That's how we learned, right? Then what we did, we relabeled that notations by selecting the generalized coordinates. So my second set of coordinates was q1, q2, dot 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 qn. Thus now I define qi is equal to fi, which is u1, u2, dot 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 un comma t for all I. Right. So what are the conditions of transformation? So this gives my generalized coordinate. So what I did is we consider a configuration space. We select the first set of coordinates. We relabel that coordinates as u1, u2, un. Then we select the second set of coordinates when we say that q1, q2, and the corresponding q1, q2 up to qn are determined. So what are the conditions for transformations? So one should remember it must have 1-to-1 mapping. And since all are mathematics students, I'm assuming you are aware of 1-to-1 mapping, and invertible. The second condition is the mapping are sufficiently differentiable. And second, the third and the last condition is the Jacobian, which is defined as the determinant of this differential upon this differential. Qj, upper is Qi and lower is Qj, should be equal to 0. So if you are able to see, I'll rewrite this. The Jacobian must have the following condition: the determinant of this differential, partial differential of Qi upon this differential, but now is it's Qj. We cannot expect I to be equal to j. We cannot expect this. It may or may not be the case, but in generally this should not be equal to 0. Sorry, please correct it. It should not be equal to 0. Jacobian should exist, it should not vanish, and the mappings are sufficiently differentiable as stated by the second condition, and 1-to-1 mapping should be present and it should be invertible. So what do I mean by invertible? It means that I can join f of I is equal to Qi of u1, u2, un, something like that. But don't worry about this condition. I have to check I messed up or not, but don't worry about the condition. This is the following condition, a transformation which you are supposed to remember. Now another so this is all about the generalized coordinates. Now so what will be, I want to emphasize this one thing which is very, very important. You need to keep this in your mind as long as you're studying physics. Generalized, oh my god, all the markers are. Generalized coordinates. Now, as you might seen so far, you might have noticed one thing. If you haven't noticed it, there is no answer. I mean, there is a question and no answer. What are the dimensions of the generalized coordinates? generalized coordinates can have any dimension. Say it does not have it is not necessary for a generalized coordinate to have the dimensions of length. The new this kind I mean this q of I need not have dimensions of length. There is no necessary condition. So this may be say angles such as theta, or it can be say phi in terms of as in the case of spherical polar coordinates, right? Or other convenient quantities. It can be anything. So it need not necessarily have the dimensions of length. This is one of the most important thing that has been emphasized on the generalized coordinates. So you can have questions like what will be the time derivative of the generalized coordinates? There is no change in that. The time derivative, there is no change in the concept as such. The time derivative of generalized coordinates are generalized velocities. They are generalized velocities, and they are represented by the q dot is equal to dq by dt, as we represent any velocity in case. These are called generalized velocity. Again, you need, once again, it should be on in your mind that the generalized velocities need not have the dimensions of velocities. Alright, it did not have the dimensions of velocities. Now, you remember from last video, you might remember I talked about the configuration space and state space. Now you will appreciate why I emphasized, why I introduced the concept of configuration or state space. It is rather difficult to visualize the motion of a system. So I want you to listen very carefully. It is rather difficult to visualize the motion of n particles, capital N particles, having n degrees of freedom. This can, however, be done by imagining the n-dimensional space, ND space, right? Which are called as, yes, exactly, the configuration space. Now you remember the concept, I hope. This can, however, be done by imagining an small n-dimensional space called the configuration space, and they are denoted by the axis of the generalized coordinates, right? As the system moves in physical space in time. So as system moves in physical space in time, its coordinates qj change, and the point in the configuration space, as I told you, the point in the configuration space represents the entire configurations of the system, right? And can be represented by some curve, right? It can thus the development of the system in a three-dimensional, yes, the development of the system in a three-dimensional space can be represented by some sort of curve in the configuration space. And this is convenient way of representing the real motion of a complex physical system by means of a trajectory in the so-called configuration space. So that's all about the generalized coordinates and the importance of why I chose the configuration space concept to be taught. So